Welcome everyone to another of our seminars in the Solar Circuit series. This is part of the HelioHub Summer 2025. HelioHub is a Discord community platform for undergraduates and recent grads interested at any level in heliophysics. And we're here to not only help you discover more in that particular field, but also connect and stay up to date on possible heliophysics opportunities. Today in our Solar Circuit seminar is July 15th, and we have a panel. We're calling it Topics in Comparative Heliophysics. The idea really here is that heliophysics is extremely important, even if that's not your particular focus in astronomy, space sciences, astrophysics, or anything really space related. But first, let me click right here. If you want to find about who's funding us, that's the Drive Science Centers. You can find more about the Drive Science Centers at science.nasa.gov/heliophysics/DSC. All right, today's topic, we're going to again look at why, even if you're astronomer, somebody studying something space-wise in a different field, you still have to have some knowledge of heliophysics. That's really kind of the topic here, the focus here. And we're going to actually today talk to various planetary scientists. And we're going to start out here, kind of close to home, actually at home, with Dr. John Bonnell. He's at the Space Sciences Laboratory where I work at UC Berkeley. So he's a friend and a good colleague. And also, taking a look a little bit further out, we have Dr. Rob Lillis, also at the Space Science Laboratory at UC Berkeley. He's going to be talking about heliophysics and its relation to things happening at Mars. And then we're going to go way out to a far, far other planetary system. We're going to talk to Dr. Howard Isaacson, also at UC Berkeley, but in the astronomy department. He's going to talk about, even though we are often concerned heliophysics with our own sun, that still gives us clues about what might be happening, not only with other stars, but also their particular planetary systems. But first off, we're going to start here at home with John Bonnell talking about some activities that he's getting geared up for. Something going to happen real soon. I don't want to steal his thunder, so we'll let him talk about that. But I'm going to stop sharing. And who do we have introducing John?
That's me.
All right, take it away.
It's my pleasure to introduce Dr. John Bonnell, a research associate and project physicist at SSL at UC Berkeley. He's been with SSL since 1999 and has contributed to some of the most impactful space missions, such as NASA Tracers, which is providing groundbreaking insights into magnetic reconnection and the Earth's near-space environment. Throughout his career, he has led the development of complex plasma instrumentation, bridging the gap between scientific theory and hands-on hardware that flies in space. His work has contributed to our understanding of the magnetosphere and space weather, and his leadership, both in research and education, has helped shape the next generation of scientists. So please join me in welcoming Dr. John Bonnell.
Thank you for that. I'm going to be all blushed now. Let's see if I can bring up. I believe that I'm sharing the first slide of my overview about the Tracers mission. Is that what everybody else is seeing as well?
Yeah, it looks great.
Excellent. Okay. So thank you. Good afternoon. I'm happy to have the opportunity to talk with y'all and share the an overview of the NASA Tracers mission. This is like most missions. We came up with the abbreviation and then backronymed it. It is the Tandem, Reconnection, and Cusp Electrodynamics Reconnaissance satellites. And I'm going to tell you about our science objectives, the details of the satellites and our team, and how we got to where we are now, which is 1 week before our launch. I want to give a quick shout out to our PI, Professor David Miles, who's at the University of Iowa. University of Iowa is the lead institution on tracers and leads a consortium of about 6 other institutions plus NASA in the design and development and implementation of the Tracers mission. So let's see. page. If I click, what do I do? Do that. Okay. All right. So what Tracers does is, so this particular slide is showing you a cartoon of a cross section through the Earth's magnetosphere, the region of space that's dominated by the Earth's magnetic field and the charged particles that are trapped on it. Uh, and in the inset up here at the top corner, I'm not sure. Can you all see my cursor when I'm pointing with it? No?
Yes,
Okay.
yes, I can.
Yes. Okay.
Yeah.
Anyway, so there's an inset up here, and the Tracer's mission is a pair of small satellites. They will be in following each other in a high inclination orbit, passes over, near the poles of the Earth, the north and south poles of the Earth, and at an altitude of about 590 kilometers. And so you might ask yourself, well, how is it that you can actually say anything about what's going on out in the magnetosphere when you're looking at something from that far down in the Earth's magnetic field? You're not touching anything out here. And the really cool thing about the way the Earth's magnetic field interacts with the solar wind, which is this out here, and the magnetic field trapped in the solar wind. This is a supersonic flow of ionized gas that comes off of the sun, flows at several hundred to thousands of kilometers per second from the sun to the Earth, and then impinges on the Earth's magnetic field. Now, the Earth's magnetic field, because there's charged particles and there's magnetic fields present, it presents a obstacle to the solar wind, and the solar wind tends to flow around and over without really penetrating in. And that boundary between where the solar wind is flowing and where the Earth's magnetosphere is in control is called the magnetopause. It's a boundary. There's an electrical, oops, excuse me, well, I'm just going to go right into this. So this is a really cool picture that's showing the way that the solar wind interacts with our magnetic field. Now, what you're seeing here is a cartoon, and that cartoon is showing how uh, the Earth's magnetic field, or the field lines of the Earth's magnetic field in blue, and the magnetic field lines that are out in the solar wind, how they can connect here near the front side and be pulled back. And when they connect like that, that allows a direct connection between the particles and the fields that are present out in the solar wind. They flow down in through this sort of funnel-shaped region that's known as the cusp. This cusp goes down to very low altitudes where our satellites can be found, and essentially takes everything that happens out here on this outer boundary and maps it down to a very low altitude so that when we fly through with our two satellites, we can see the current systems that are flowing in response to this reconnection activity, the protons and other energetic particles that are coming in along the field lines. And all of those things tell us something very interesting about where the reconnection happens, over what sort of region, or distance along the boundary it's happening, and whether it's sort of sitting static or moving around. And by looking at how that happens, as a function of how hard the solar wind is blowing, how fast, how dense it is, and the orientation and strength of the Earth's magnetic field, it'll allow us to then really map that out in a way that hasn't been done before. Before, there have been missions that have looked right where that reconnection is happening. They understand a lot about the physics that make that magnetic field line breakage and change happen, but they can't say anything about what's going on across this huge boundary that's sitting out maybe 120,000 kilometers across. So that's what Tracers was to do. That's what we will do when we get up. And to give you a sense of what this looks like when we fly through, can I click on that? Yes. Okay. So one of the things that we will see, so here in this center part of this, we have another cartoon. The cartoon is showing again a cut. The sun is to the left, the earth is to the right, and this is a cut in the noon midnight meridian. You can see that one of these magnetic field lines has been reconnected. Eventually it'll swing back over and go to the back. You get energetic particles that flow in along here. And depending on whether, what's happening out here, the whether the reconnection is steady or is moving along the magnetopause, you'll get different patterns of ions and electrons coming down. They will end up at different magnetic latitudes. And that's what's being shown here, is that across the bottom, you can sort of think about this as the horizontal component. This is in geomagnetic latitude. The vertical axis on here is the energy of the particles, and then the color scale tells you how intense the flux, the number of particles per square centimeter per second that are flowing. And as we go from low latitudes up to higher latitudes, we see first high energy particles and then lower energy particles. And this has to do with when you release a cloud with a mixed energy of particles in it, the highest energy particles come down first, um, closer to the equator, and the lower energy particles come down further up. And depending on whether this is sort of sitting static, one way that I like to think about this is if we can fly through it with our two satellites and we basically see the same pattern of high to low at the same latitudes, it's like we're running under a static waterfall. The source is sitting there, we're flowing under it, and we see it at the same place in space. But if instead this reconnection site is moving or is forming and reforming at different places, what that's more like is how if you've got a rain cloud, the rain cloud is moving across the ground, and if you have two satellites that come through or two observers that come through, they'll see it at one latitude, the next one will see it somewhere further up the path. And both of those possibilities are, they're given by models and things. And so we need to go and see how that works over different conditions in the magnetosphere. All right. So, what's the thing, what do the satellites look like? All right. So this is a cutaway schematic of one of these satellites. These satellites are not very big. They are about a meter across, so about the size of a card table, and about 50 centimeters top to bottom from their top deck to the bottom deck, with a little skirt of extrasolar arrays that extend down a little bit further. They spin around this central axis, and they carry, in addition to propulsion systems and radios and batteries, in order to support all the scientific instrumentation, we carry several different kinds of instrumentation. We carry two different particle detectors, the the analyzer for cusp ions, the analyzer for cusp electrons. These detect the flux of energetic protons and electrons that are coming from different directions at different energies. And then we have a variety of uh, instruments for measuring the different parts of the electromagnetic field. We have three different types of magnetometers. Uh, one from UCLA, the MAG, one from Iowa, the MAGIC Tech Demo, and the magnetic search coil, also from Iowa. These are for measuring low frequency and DC magnetic fields and higher frequency ones. And then finally, there's the electric field instrument, which is the one I'm responsible for. We measure two components of the electric field, the components that are perpendicular to the local magnetic field that are associated with the flows and momentum transport from the magnetosphere down into the ionosphere. And these are done with deployable booms that you'll see a cartoon of later on. So that's what that looks like. And in addition to that, um, in order to in order to provide ourselves with some context for how all of this comes together, we have a simulation and science team. We do modeling and to understand how the field line is connected up. We have a team of about 100 to 200 folks, depending on where we are in the time frame. We started working on this back in 2020, started the proposal back in 2016, so we're looking at about a 9-year life cycle here. Let's see, and we wouldn't be anywhere without our original PI, Craig Klutzing, who was a professor at the University of Iowa. He unfortunately passed due to cancer back in 2023. He was an avid musician and guitar player, and we're really glad to be carrying two of his favorite guitar picks mounted on our electronic boxes as a memoriam to the warmth and guidance that he gave us for this mission. Just to give you a sense of how these things come together, we first assemble all the instruments onto sort of what's called a flat sat. It's a skeletal thing that allows us to put everything, check all the electrical harnessing. This gives you another sense of the scale of the vehicle. Again, it's not very big. Things are very tightly packed, and this is the some of the instrumentation that's being installed down at our spacecraft contractor, Millennium Space Systems, in fabulous El Segundo, California, down near Los Angeles. And to give you a sense of what these will look like on orbit, they will be spinning. This is roughly to scale. I think the booms are actually a little bit longer relative to the body of the spacecraft than what's shown. The spacecraft will never be this close together on orbit, but it gives you a sense of roughly how fast they spin and what they will look like when they're operational in orbit. Another nice shot. This was probably from vibration testing when we test how well the satellite stands up to the vibration loads that it feels during the launch. We are flying as the primary ride share on a Falcon 9 launch that will be carrying probably dozens of other CubeSats into orbit. We get stacked up, we get put on top as sort of the cake topper, and then we will be here. We'll do this launch from Vandenberg. I believe this is the Vandenberg launch site, and our launch will be happening hopefully next Tuesday, the 22nd. And we're looking forward to getting things commissioned in about a week and after that, and being fully up for science about a month after that. And that's Tracers. Tracers is all about understanding how the Earth's magnetic field interacts with the solar wind. So that's part of this whole solar circuit, so to speak. With that, I'll take any questions that y'all have. Otherwise, or actually, I guess we're supposed to wait till the end for questions. Is that right?
Usually we take one, maybe two. Let's take one, and then
Okay.
we'll move on to Rob. But yeah, anybody want to ask a question of John? I mean, I started to think of many here. Go ahead and speak up. Otherwise, we will move on. But
They want to hear about Mars.
well,
Mars is cool.
come on,
Mars, even though it's barren, it's cool.
those tracers. But okay, quickly for you, you showed that animation of first of all, I thought magnetic reconnection was always when field lines touch, and then I got the impression here that you were showing them breaking. But it's
They
when
do
field
both.
lines. It's
They do
both.
both.
Okay.
So you have two field lines that are, at some angle with respect to each other. And what happens is that they there's a electromagnetic interaction that happens at the place where the shear is strong, and all of a sudden the field lines are now connected with each other in a different way.
In a different. Okay. Okay.
The top, the to use the technical term, the magnetic topology changes, and a field line that had its, that started at the surface of the Earth, went out to the magnetopause and comes back to the Earth, now finds itself going out into the solar wind, and in the bottom going out into the solar wind. And so you've opened the field line, solar wind material can come in, the flow of the solar wind across that magnetic field line can help drive currents that then flow down into the ionosphere and make the ionosphere move. So there's opening things up means not more, you're not just letting in the material, you're letting in currents that then can move things around.
Well, okay, so that was my real question because the animation showed every time a field line got cut, a new one
Yes.
sort of grew out, and
Yes.
but that's true. That's not.
That's one, that's the so a good way to start an argument with space physicists is to ask the question, are there really magnetic field lines? And
Oh
some
my goodness.
people, and exactly what are we seeing and what are we trying to represent with this? And there's a lot of different ways to look at it, but essentially, yes, there are processes that can be interpreted as moving field lines, continuing to sort of move field lines back up to the magnetopods that then get connected into ones in the solar wind. They get folded back, and then the process continues in a cycle.
Interesting. Okay, great, great. Well, thank you very much, John.
You're
Uh,
welcome.
yeah, now we're going to take a trip to Mars and look at the somewhat, actually very different magnetic field lines out there at our neighbor planet. Who do we have introducing Dr. Lillis?
That's me.
All right.
Um, okay. Dr. Robert Lillis is the Associate Director for Planetary Science at UC Berkeley's Space Sciences Lab and Principal Investigator of the Escapade Mars mission. He's also a key science team member on NASA's MAVEN mission and the Emirates Mars mission. With a PhD from UC Berkeley, his research focuses on Mars magnetic fields, atmospheres, and space environment. Please join me in welcoming Dr. Robert Lillis.
Fantastic. All right. We can
I'm
already
still on
see.
mute. Okay. Thank you, Claudia. Can you guys see the correct screen or are you seeing the other one?
Now we see it.
Okay, good one. Okay, great. All right, so I'm going to give a quick overview of the Escapade mission, what it is, what it's trying to do, and it's sort of essentially trying to understand many of the same processes that John talked about, except at a very different planetary environment. Mars, the biggest difference is that Mars does not have a global magnetic field, and I'll get into that. So first of all, just briefly, what is Escapade? Escapade is a two spacecraft mission, so a bit like tracers in that sense. It is much, much lower cost than most missions to other planets. It's about 60 or 70 million compared to 600 or 700 million. So it's about one-tenth of what NASA would usually spend. And it's dedicated to understanding how the energy and momentum from the solar wind are transferred into and throughout the Martian magnetosphere and how that interaction helps to drive different kinds of atmospheric escape, which have contributed overall over the course of solar system history to Mars transforming from a place that was at least episodically warm and wet, had a much thicker atmosphere, to the dry planet there is today, where the atmosphere is too thin to support stable liquid water. Here's just a bit of a timeline across the bottom. We've been working on this. We wrote the first initial proposal in 2016, so actually similar to tracers, we've been doing this for about 9 years now. Okay, so why do we need Escapade? And the most obvious reason is that a single measurement platform leaves major questions unanswered. So let's just look over on the right here. We have a schematic of the interaction of the solar wind with Mars. The first thing that you'll see is that because Mars doesn't have a global magnetic field, the solar wind is not kept many, many planetary radii away like it is on the Earth. For Mars, the only obstacle to the solar wind is the conductivity in Mars's upper atmosphere, particularly its ionosphere, that ionized layer in the upper atmosphere. And so Mars does have a bow shock, but it's a very different bow shock. It forms only about 1.6 Mars radii upstream from the planet, up to 1.8. And so what happens is that interplanetary magnetic field that's frozen into the solar wind, it encounters this obstacle and it piles up in front of and then drapes around this obstacle, giving Mars this sort of magnetic pileup region here. You can see yellow is the ionosphere, and then in the back here we have this two-lobed, meaning two different directions of magnetic field towards and away on two different halves of what's called the magnetotail. And there's all sorts of connection and reconnection that happens because while Mars doesn't have a global magnetic field, it does have crustal magnetic field. So these are fields that are a result of very large, coherently magnetized volumes of crust on Mars. At least at orbital altitudes, these are many times stronger than they are on Earth. So that they really are a feature of the Mars-solar wind interaction. And as Mars rotates, those fields can connect and reconnect with this draped, induced magnetic field to produce a lot of magnetic reconnection, aurora, etc. So to understand this system, we've only had single spacecraft up until now, and if you travel in the system and you can only measure things that are existing where the spacecraft is, these are not remote sensing measurements, they're in situ measurements where the spacecraft is at any given time. If you see something change in your data and you only have one spacecraft, you don't know whether you've just witnessed a global change or you've just entered a new plasma region. Those two things cannot be distinguished, but with two spacecraft, you can. And also, if you only have one spacecraft, either you can be in the upstream solar wind monitoring the space weather environments, the sort of inputs to the system, or you can measure the effect of those inputs. But you can't measure that cause and that effect at the same time with only one spacecraft. But with two spacecraft, you can. So the solution is indeed multi-point in situ observations from coordinated orbits so we can untangle that spatial from temporal variability and characterize the real-time response to space weather. So there's all sorts of different plasma phenomenon that are observed at Mars. I'm not even going to describe these six, actually, because these are just six out of maybe 30 or 40 that I could talk about. But there's a really quite diverse, rich electromagnetic and dynamic plasma environment around Mars. We have this ion escape plume. We have a very complicated system of global currents. This picture doesn't even capture half of it, honestly. We have dynamics of electrons as they're bouncing back and forth. But on Earth, they would bounce from North Pole to South Pole. On Mars, they could just bounce back and forth between two nearby regions because we have these localized crustal magnetic fields. We also have aurora that are produced by electron acceleration that can move over time. This is a time lapse of about 15 minutes showing how that band of aurora moves. We have a twist in Mars's magnetotail. We don't fully understand exactly what that causes, but probably the crustal magnetic fields, and that itself is dynamic. Then we have various other processes. This is just one of them, this so-called snowplow effect. Anyway, all of these are dynamic in space and time, and a single spacecraft cannot distinguish between them. And it only takes a solar wind disturbance, maybe 1 or 2 minutes, to propagate through the system. If you only have one spacecraft, such as the prior Maven mission, you have to wait for more than an hour. So having two spacecraft is it's a really sort of a quantum leap in how well we can understand the system. Escapade's three goals, they're quite related. Goal A is just to understand the structure of the magnetosphere and how that guides ion flows, particularly this plume escape and tail escape here. The second goal is to understand how energy momentum flow from the solar wind across the bow shock into the magnetosheath, across the magnetic pileup boundary from the sheath into the tail. So all the different ways in which plasma flows throughout the magnetosphere. And then goal C is to understand how matter flows into and out of the atmosphere. So ions can be both accelerated into the atmosphere and can also escape from the atmosphere. When they're accelerated into the atmosphere, they can actually splash out other particles, almost like a kid jumping into a pool and the water goes everywhere. You can escape ions that way too. We have a bunch of instruments on board, a relatively small payload, but focused. We have a magnetometer on a boom, much like Tracers does, although we only have one per spacecraft, not three. We have an electrostatic analyzer that can measure both superthermal ions on the right-hand side, electrons on the left-hand side. We have a Langmuir probe to measure the thermal plasma, meaning the low energy plasma. So we measure electrons with these needles. We measure ion densities with these golden plates. We measure spacecraft potential, so how charged up and down the spacecraft gets with this golden sphere here on a stick. And we also, just for bonus, we also are carrying cameras with which we're hoping to see aurora. What do the spacecraft look like? So this is what it's called. It's from a company called Rocket Lab, who are known for making rockets, but they also make spacecraft. And these are where all the instruments are placed. This is the instrument deck here. This is the magnetometer at the end of the boom. These are the needles on the Langmuir probe. And then we have the ESAs here. We have the floating potential probe here. And we have these two golden squares for measuring ion density. Then we have all the other subsystems that the spacecraft needs to stay alive, record the data, and beam it back to Earth. Our team is much smaller than the Tracers team. This is the science team is on the smaller side, maybe only kind of 15 people. We have probably up to 200 or 300 people total at any given time have worked on the mission, particularly at Rocket Lab. because they have a big workforce there. And you can see most of this is blue. Blue is UC Berkeley because Berkeley is handling the science leadership, the project management, the mission systems engineering, the finance, the schedule, the mission assurance, the instrument digital processing unit, those ESA instruments, the mag boom, the navigation, the operations, the integration and test, and the science data center. So it's very largely a Berkeley mission with some key partners as well. Picture of the science team. We have a beautiful view from SSL. In case those of you have not been here, I strongly encourage you to visit. It's great. Okay, so where were we last summer? We were hoping to launch last fall, and we had the spacecraft had gone through their environment campaigns. This is a vacuum chamber here. This is the engine nozzle for one of the spacecraft. They were finished up around mid-August. These are the two completed spacecraft here, and the team that built them. Here's me and the project manager looking very proud in front of the gold spacecraft. They're called blue and gold, by the way, because those are the colors of UC Berkeley. They left Long Beach, where Rocket Lab is, on August 15th. They arrived on August 18th by FedEx in Florida, and we gathered around to welcome them. This was the spacecraft being unloaded from the truck and forklifted down, brought into the integration facility, quickly put on purge. Purge is just when you keep a flow of dry nitrogen into the instruments to keep them clean. And we were testing in the clean room before putting fuel in the spacecraft, but then and at the same time, the New Glenn rocket from Blue Origin was also being prepared. This was, I think, a fit check on the launch pad. And this was our mission plan, was to launch no earlier than October 13th last fall, and to take a direct 10-month cruise to Mars like this and arrive in September 2025. This year, however, was postponed. We were very, very annoyed because we had been looking forward to it. But these things happen in the space business. Delays happen all the time. So a bunch of media about this delay. The delay was essentially because the Blue Origin rocket was just not ready, and Earth and Mars were only going to be lined up until about October 21st. And after that, the planets would have moved too far from each other to make it possible to launch at all. So there were all these articles about it being delayed. So why? So yeah, it was deemed unlikely to launch, and we didn't put fuel in the spacecraft because it only keeps for 2 or 3 months on board before. If you don't launch, it's very difficult and toxic to remove. So now Mars arrival is pushed back by 2 years because it takes Mars and Earth another 2 years, 25 months to be exact, to get into the right alignment again. So we're going to be launching this fall, and we'll probably get a couple of months notice of when we're likely to actually launch. And okay, so we have to kill time. We got to kill about a year after we launch before we can actually go to Mars. And up here on the right is our path near Earth for about 14 months before we head to Mars in November of next year. And so we have this big kidney bean shaped orbit that we follow that'll go much further away than the moon. I think it's about 6 million kilometers from Earth at its furthest. And this will be interesting in some ways because we will be passing through the Earth's very distant magnetotail. Now, John showed a picture a bit like this. The Earth does have a magnetotail, which can stretch a long way, but we've never measured the Earth's tail further than about 200 Earth radii. And we're going to be passing about 300 Earth radii. So we have no idea what the tail even looks like out there. How prominent is the structure? What's the dimensions of it? Do we see magnetic reconnection? How often do we get plasma being accelerated towards or away from Earth there? And how and with what time delay does this distant part of the tail respond to upstream changes? So we're going to be doing some real discovery, fun science, bonus science before we get to go to Mars. Okay, then we head to Mars starting in November 2026. We get there in September 2027. And then we go into this, we do a Mars orbit insertion burn where the spacecraft have to fire their engines for about 10 minutes each to slow themselves down. Then we establish the first ever Martian formation flying around Mars. That'll take a few months. And then eventually we start what's called Science Campaign A in June 2028, where much like tracers, the two spacecraft are in the same orbit following each other like a pair of pearls on a string. And this is optimized for studying how the Martian magnetosphere changes on short time scales. So the time difference between the two spacecraft will be between 2 minutes and up to 30 minutes, and it'll go back and forth. So we can really tell how the system varies on short time scales. Then after about 6 months, we will raise and lower each of the orbits respectively, and then the two spacecraft orbits will be now one will be longer than the other, so they will what's called precess, i.e. be twisted by Mars's gravity differently from each other, and the two orbits will separate, allowing the two spacecraft to be much further from each other and hence to measure simultaneous plasma measurements in different regions. And here is a nice video that Goddard put together with our help, including my colleague Ying Juan Ma, showing the two spacecraft orbiting Mars. The sun is in that arrow direction here. And the green is that's electric currents. The white little tadpoles are solar wind protons being deflected around the magnetosphere. And then those, the orange are magnetic field lines. And this is just simulating a few hours of a particularly stormy solar wind time, showing how the system varies pretty rapidly, and the two spacecraft are going to be flying through it. Those are those two little blue tadpoles, and we're hoping to use those short temporal distance from each other measurements to understand this system. And these are how the two spacecraft will be oriented as they go in close to Mars. You can see the altitude there. These are two different kinds of orientation. You can see one is optimized to be able to see Mars and anti-Mars and the spacecraft's direction, and the other is optimized to see Mars and the spacecraft direction and the sun. So we're going to be alternating between these three because we'd love to see every direction at once, but that wasn't possible because we couldn't afford to put the instrument on a boom we would have liked to. So we're doing this instead. Okay, and that's my last slide. So Escapade is the first multi-spacecraft science mission to orbit Mars, or indeed to orbit any planet other than the Earth or Moon. And we're going to be able to really understand the plasma environment and characterize that chain of cause and effect that affects the Martian magnetosphere. So we're looking forward to launch and to doing some unique science at Mars and along the way as well. And if we have time, there's a very cheesy trailer that would be fun to play, Dan, if we have time. It's about a minute long.
Yeah, okay, let's save it to the end.
Okay, got
But
it.
fantastic. Thank you so much, Rob. Any questions for Dr. Lillis? We'll take one or two right now. And then if everybody can stick around, we'll definitely leave the rest of the remaining time for Q&A.
Hi, my name's Arya. Thank you so much. That was super cool. I wanted to ask how you anticipate Escapade's findings will complement or build on previous Mars's missions, like Maven, for example.
That is a great question. Yeah, in fact, it's I think the one thing that we don't understand based on Maven observations is we don't really understand how the system varies on short time scales. We really don't. Maven has done a very good job of giving us this average picture. I think one of my slides earlier showed that, meaning that like we can go and, for example, measure the solar wind upstream, and then 2 hours later we can measure some process that happens, let's say in the magnetotail or in the ionosphere. And so we can sort of see, well, okay, usually when the solar wind or the interplanetary magnetic field is in this particular orientation, the conditions tend to be on average something like this. But we see an order of magnitude or more variability typically. And as Maven is traveling through that upper atmosphere, we see things change. But as I mentioned, we don't know whether we're seeing global changes or we're just seeing different, regions. So that spatial from the temporal variability has really been impossible to disentangle. And so it'll be like opening a second eye, like almost getting like a stereo perspective. That's what I think Escapade is going to add. And what are we going to find? I don't exactly know until we get there and see it. And that's part of the fun of exploration.
Well
Thank
put.
you so much. That's awesome.
All right, maybe one more question if we have it. Nope. All right, Rob, we're gonna save your little extra tidbit for the end here.
Sounds good.
And now we're gonna go to the exciting world of exoplanets with Dr. Isaacson. Who's gonna introduce our final presenter here?
Yeah. Okay. So our last speaker is Howard Isaacson. He received his undergraduate and master's degree at the Physics and Astronomy Department at San Francisco State University. After graduation, he began working at UC Berkeley on the Kepler Space mission operated out of NASA Ames Research Center, searching for life in the cosmos. He is currently pursuing his PhD at the University of Southern Queensland, Australia, and holds a research position split between two research groups. The first is the Moving Universe Lab, focused on creating a web portal to identify possible systems containing stellar mass black holes through microlensing events. And the second is the California Planet Search, characterizing exoplanets discovered that are most like the Earth. Howard is also interested in studying the timescales of stellar activity in a star's chromosphere. Please welcome Howard Isaacson.
Thanks, Phoebe. Very lovely introduction. Appreciate that. And an update to my introduction. I finished my PhD as a non-traditional student earlier this year. I have to update my webpage, I think.
Yeah, that's
For all the non-traditional
Sorry
students
about
out there, there's always hope for you to get to finish that kind of thing. All right, cool. Well, thanks everybody. Dan, thanks for having me. This is great. It's been a while since I've seen you, and so it's nice to see you again after some time's passed. I'm going to talk about the exoplanet side of heliophysics and helioscience. So, we know so much about our sun because it's close to us. We can take resolved images. We can take high resolution, high signal to noise spectra of it. When we want to learn about planets around other stars, exoplanets, we need to use the most sophisticated telescopes and instruments that we have on Earth to do that. And here are a few of them to start us off. This is the Kepler Space Telescope. It's now retired. It's out in space floating around the sun. There's the brand new James Webb Space Telescope right in the middle here, and the TESS spacecraft, which is in an orbit that circles the Earth in about distance of the moon to collect exoplanet observations. And so as an observational astrophysicist, astronomer, I've always been interested in using these types of telescopes, and even more so from using the telescopes that are located on the ground. So these are a couple of examples of some ground-based telescopes. Bottom right here is the automated planet finder. This is a robotic telescope down near San Jose, California. It opens up every night. You feed it a star list and go to bed, and then in the morning you wake up to data. It's really quite an exceptional piece of instrumentation. On the left-hand side are the Keck telescopes, Keck 1 and Keck 2. These are situated on the top of Mauna Kea in Hawaii, in the Big Island. They're at 14,000 feet above most of the Earth's atmosphere, providing a really wonderful view of the night sky. And we use these all the time to collect information about the stars that host exoplanets. So one of the main things to try to focus on what we know about exoplanets from their host stars. One of the first things that we can learn about them is an exoplanet's size relative to its star. So if you have a planet of, say, 1 Earth radius, and it's basically the size of the Earth, and you put it in front of a large star like the sun, or say an average star the size of the sun, it produces a relatively small transit. But if you take that same small planet and you shrink the star down, when it crosses in front, when it transits its host star, the signal that we see is larger. We see a larger dip in light because more of the star's area is blocked. So one of the first things we can learn about planets from their stars is how big they are relative to their host star. We do this from the transit method. Kepler was excellent at this. The TESS Space Telescope is excellent at doing this. And we use things like the James Webb Space Telescope for further follow-up there. This is a really great example on the right here. This is the sun, a depiction of the sun compared to what the star TRAPPIST-1 might look like. This small star is only 1/10 the radius of the sun, and it's got 7 Earth-sized planets around it. So it was relatively easy to find these small Earth-sized planets around this tiny star, just because the ratio of the planet to the star is so much smaller. So again, one of the first things that we can learn about a planet from its star is just how big it is. One of the next things that we can learn about exoplanets from their stars are how far away they are, and often that leads us directly to the temperature of those planets. So in our solar system, Mercury is closest, Venus is next, then Earth, and then Mars. And most of the systems that we know about that host exoplanets around other stars, they are much closer in. So those are depicted around this smaller star, Gliese 581 is its name, and these planets B, C, D, and E. And the idea is that these smaller stars, they give off less energy. If you want to get to the same temperature as you move away from their star, you have to get closer in. Those planets that are closer in are warmer than they would be. They're closer in, and they're still in the habitable zone. Whereas if you're around a star like the sun, you have to be further away. This makes them more amenable to observation, It means that they're going to transit more often. It means that you can measure their mass more easily. And so a lot of different exoplanet exploration programs are focused on the smallest stars, similar to Gliese 581 and the TRAPPIST-1 M dwarf or red dwarf that I mentioned earlier. So just to summarize that, the larger the star, the further away its habitable zone is. The smaller the star, the closer it is to its star, making it easier to observe. So one of the most amazing results from the Kepler Space Telescope, among the many, many great discoveries that it made, was that it measured the average occurrence of planets that are about the size of the Earth that are in the habitable zone, their own star's habitable zone. And of all the planets and stars that it measured, the end result was that about 1 in 5 stars that are similar to the Earth has a planet that's about the same size and about the same orbit. And this is just such an incredible discovery, right? And this means that, you know, almost every single star out there like the Earth has a planet like this, let me try that again. Almost every single planet like the Earth is out there around a star like the sun. And, you know, just to know that from, ancient days when people thought about maybe there's planets out there to, a few decades ago when it was like, well, maybe there's other Earth-like planets, to knowing that, the majority, and not the majority, that most stars out there have planets like the Earth is really an incredible discovery. And we know this because we can measure, their orbital periods, which tells us how far away they are from Kepler's laws. And so, the host star is really the critical starting point in understanding all of these planets out there. So one disadvantage we have in exoplanet science is that we don't have really great photos of the exoplanets that we discover. So this graphic is hot off the presses. This is the first light image of the Vera Rubin Observatory, which is just produced last month. So it was, as these other space missions that were talked about before, decades in the making. And the first light happened just a month ago, and here's one of them. We don't get this with exoplanets. I wish we could produce this kind of publicity for exoplanets when we're studying them and show people the continents on them and the clouds and oceans and things. But instead, we give these lovely depictions, which are sort of the focus of my research, which are high resolution spectra. So on the left-hand side here is one of the newest instruments, the Keck Planet Finder. This is a high resolution spectrograph that sits at the Keck Observatory. It's used to measure the spectra of stars in an incredibly detailed way. Every star has sort of a fingerprint of a spectrum. We can study these. We can differentiate one from another. We can figure out how large they are. We can figure out their temperatures. We can figure out their metallicities, meaning what components they have, like iron and sodium and nitrogen, as depicted here. And to say a little bit more about spectra themselves, there are absorption spectra, which means you have sort of a hot source with things like iron or sodium subtracted out some of the light, or you have an emission spectrum. And then depicted right below each of these is when you have fewer portions of the spectrum are illuminated. Think of the orange lights that are street lights at night. These are orange sodium lights. They're orange because sodium is orange. That's an emission spectrum all in itself. So when we think about how we understand these in the space context, the exoplanet context, we're thinking about stars as an absorption spectrum and potentially, planets also in absorption, but it's completely convoluted with the star spectrum. To complicate this even further, we do this on top of a mountain that's right next to an active volcano at the Keck telescope. This eruption happened at the same time that we were doing commissioning for the Keck Planet Finder, just adding a little bit of spice to the adventure that is ground-based astronomy. That's Mauna Kea, where the telescope is, just across the lava pool in that big valley there. Okay, so because we have these great telescopes on Earth and we can get high resolution spectra of the stars, we identify the best targets that are out there to do space-based astronomy with them. Because these really exceptional resources, like the James Webb Space Telescope, you can only get the very best candidates to observe with those because the time is just so limited. So we use the ground-based instruments to find the best targets. We use the space-based instruments to follow them up. And one of the main ways we follow up exoplanets with the Webb Space Telescope and with Hubble before that is by taking a spectrum when the planet is crossing directly in front of its star. So this is a transmission spectrum, right? Imagine that if the planet is so faint next to the star that you don't get any kind of light from it, no reflected light off of it, It's only when some of the star's light passes through the atmosphere of the star, excuse me, let me say it again. When some of the starlight passes through the atmosphere of the planet imprints its own spectrum onto the starlight. So essentially we take two spectra. First, we take one of just the star, then we take one of the star plus the planet, and you subtract off the stellar spectrum, you're left with the planet spectrum. And so by doing that, you can do the same practice that we did in the previous slide where you have sort of sodium or oxygen, you can detect those elements in the spectrum. And with the Webb Space Telescope, you can do molecules. You can do things like detect whether methane or carbon dioxide. This depicts dimethyl sulfide. Ammonia is really common in exoplanets. And sort of finding the right blue curve here, the model that fits each of these white data points is really tricky because you can see that this model is really detailed. There's lots of squiggles up and down, and these white data points don't always necessarily land right on the model, which means maybe the model's not quite right. And so a huge part of the analysis process is trying to find the right combination of molecules that match the spectrum so you can definitively say, this planet has methane in its atmosphere. And of course, what we really want to do is find out even more exotic things like water and oxygen. So again, we don't have the great capability of imaging exoplanets. This bottom left image is of a galaxy from James Webb Space Telescope. Total postcard. It's great, just an incredible image in itself. We have all these white dots that we draw lines through and try to understand what they represent. Do they represent water? Do they represent sulfur, carbon dioxide, ammonia? And you can see there's even places where there's gaps in between the data points, like between 2 microns and 3 microns. Just think of these as different energy levels or different colors of the star. And when we have those gaps, we have to just do the best we can to use the data that we have on hand to infer what's in between those, to use the data we have on hand to choose between the best model and maybe the next best model and try to say something definitive about the planet's composition. Just to emphasize one more time how hard it is to figure out what these spectra mean, this yellow model here that goes left to right and the blue model are two models that could potentially fit this data. And what this plot is trying to show is that when you have all of these white data points, the actual measurements themselves from Webb, they kind of match both of these models equally well, or you could even say equally poorly, right? There's nothing that's distinguishing the two models from one another. And so in this case, you can't even say something like, we're sure it has a water-rich atmosphere, or we're sure that this signal is due to star spots. And so people are always thinking about the next best telescope, even though Webb is brand new. What's the next best thing we can do? How do we fill in these gaps? How do we get higher resolution? How do we get a bigger telescope? And the reason for that is that we want to find something like this. This is very cartoony, but just showing what an Earth-like exoplanet transmission spectrum is. So all the transmission spectra I've shown so far are sort of giant planets, or maybe at their smallest, they're 3 or 4 times the radius of the Earth. But we really wanted to get to the point where we have such good resolution and such high quality instruments that you can say, now we see ozone in the spectrum, now we see water. Now we see methane and oxygen and water and carbon dioxide, and that's starting to resemble something that looks like the Earth's atmosphere. But of course, this is downline. This is, the future of astronomy. This is people who are on this call now working on these types of missions someday. And one of the missions, like the next biggest and brightest thing, right? We're always on to the next shiny object, the next thing that can do the next best job for astronomy, and that's the Habitable Worlds Observatory. They haven't even picked a concept design yet. There's still a couple different options out there that they're going to choose from. We're still working on figuring out exactly the right thing to make the right telescope. We're early on in this process. Opportunity knocking for people out there who are undergraduate students who want to go into engineering and astronomy and physics and things like that. So I'll end right there, but yeah, the opportunities to explore exoplanets, learn more about them are vast. There's incredibly fun and interesting problems trying to be solved out there. And yeah, it's a lot of fun.
Fantastic. Thank you so much. All right, let's open the floor for questions for Dr. Isaacson.
Hi, I have a question. So, last semester I did a project with the 1 meter observatory at the Embry-Riddle University in Daytona Beach, and my project was on M-star habitability. and calculating habitability zones. And one of the things that I investigated was how we're able to find these HC zones or these HC values. Have we considered looking at different ways of when we consider stellar flares? Because M stars are very convective and they have a lot of CMEs and a lot of solar activity. What kind of formulas, or at least what kind of instruments, do we have to actually look at more than just assuming at like very Earth-like habitats and stuff like that? At least with more convective atmospheres or convective stars like M stars.
Yeah, great detailed question. That's really an interesting one. So all of the habitable zone depictions that I discussed are that very simple model that you described. You just figure out the period, which tells you the separation, you know how hot the star is, and that tells you some temperature simply based on distance from the star. But these more complex studies that you're talking about, and it sounds like the one that you were a part of, they really get detailed, right? They're really able to sort of understand not just where that planet is at right now, but they're able to integrate that star's habitability over billions of years. So they say, okay, well, did that planet move inward or outward? Did that star create so many flares that it's blown off the atmosphere? Maybe the atmosphere had to either maybe there's still an atmosphere and M stars are horrible host stars and they're never going to find any good candidates for Earth-like planets. I think they have good data on this type of thing from missions like TESS. You can do, because the time frame is long, you can do focused observations with X-ray telescopes to learn more about that. But yeah, it's a really interesting part of getting more detailed understandings about M stars and their habitable zones. Yeah, great question.
Okay, thank you.
Great, thank you, Ainsley. Reminds me of the upcoming Pandora mission. Do you know anything about that? Are you excited about that?
I am excited about. Oh yeah, go
Wait,
ahead.
I'm sorry. Were you talking? I don't know,
well,
Dan.
yeah,
Were you
either one
talking
of
to
you
me or were
go.
you talking to Howard? I'm sorry
Ainsley
about
probably knows more
that.
about it than I do. Go ahead, Ainsley.
I actually don't know about that. Could you elaborate a bit more?
There you go.
I only know a little bit about it, but I'm excited about it. It's a CubeSat that's going to measure stars. I'm not sure if it's going to look for just transits or stellar activity or both, but it's a CubeSat, so one that's a small scale, capable of doing some testbed and measurements that could potentially lead to like another big satellite, more capable instrument. But maybe Dan knows some more about it than I do.
No, I was only just reading about it yesterday, so
Yeah, it's super cool.
yeah, it did sound very cool. By the way, what was really cool was you had that picture of KPF. The team here is very quiet. They don't really market themselves too well. Can you send me that picture? I've never seen a picture of KPF before.
This one here?
Yeah.
Yeah, so just to say a little bit more about it, this instrument, this is like a camera up on top here. These pieces hold optical instruments. The part that sort of looks like it's glowing is the optical bench, and typically these are made out of metal or some kind of metal that doesn't change very much with temperature. This is a piece of what's called zero dur. So this is a ceramic glass composite that has very minute changes in size due to changes in temperature. So it's used for things like space telescope mirrors, like HST or something like that. And the idea is that you want to create this really stable instrument because they're measuring really, really tiny changes in the star spectrum to measure the mass of the planets. And so you build it on this optical bench that has almost never changes, even if it has small temperature variations. And so that's why it's kind of glowing from underneath, as it's a piece of ceramic glass. It's cool.
Yeah. They need to share that with more of their team members. That's fantastic. Thank you, Rob. Thank you for sending the link for that trailer. I'm going to share it with everybody here and also in our HelioHub Discord. So please take a look at that. I'm sure it's fantastic. And with that, I'm also going to stop the recording. So thank you so much, everyone, for your presentations, Dr. Bonnell, Dr. Lillis, Dr. Isaacson. We really appreciate that. This was really great, and for everyone who attended. And hopefully we'll see you next week. We'll, again, stay in touch with us on our Discord, HelioHub Discord. We'll tell you about next week's presentation in the solar circuit. Thank you, everybody.